Welcome to the Explainer. Today we're tackling a massive, classic algorithmic mystery from LeetCode. It's called Find the Duplicate Number. But look, we're not just going to skip straight to the answer. We're going to put on our detective hats and use some Socratic deduction to uncover this thing step by step. It's a genuinely thrilling mystery, and by the end of this, you'll see how beautifully complex math can collapse down into an incredibly elegant solution. So let's just dive right in.
So here's the setup. You're given an array of n plus 1 integers, and every single integer is somewhere in the range of 1 to n. We know for an absolute fact that exactly one number is repeated, although it might be repeated 1, 2, or even more times. Okay, I actually want you to pause for a second. Think about it. What is your immediate gut reaction for how to find that duplicate?
If you're like most people, your very first instinct is probably to just build a frequency map, right? You just count how many times each number appears. Boom, easy. But the strict constraints of this problem totally block that easy path. We are strictly forbidden from modifying the original array, and we're restricted to constant O of 1 extra space. A frequency map, well, that would require O of n space, so that whole approach just goes right out the window. We're going to need something way more clever. To solve this, we honestly need a major paradigm shift. Let's forget about arrays and hash maps for a second. We've got a classic pigeonhole setup here. N plus 1 numbers, all between 1 and n. That means one bucket is guaranteed to get 2 pigeons. But what if we stop seeing these numbers as just static, boring data sitting in a box? What if we start viewing each value as a directional pointer, literally telling us where to go next?
Okay, let's trace this out mentally. Imagine you start at index 0. You look at the value sitting there, let's just call it v. Then you jump to index v. You look at the new value there, and you jump to that index. If we have an array like 1, 3, 4, 2, 2, and we start jumping from index to index based on those values, what actually happens? We're chasing pointers. And eventually, because a number is duplicated, multiple indices are going to point to the exact same destination. Now, at this stage in our Socratic deduction, you might be having another really common instinct. Since we're dealing with duplicates and matching pairs, couldn't we just use the classic bitwise XOR trick? You know the one? XOR all the array values together, then XOR all the indices from 1 to n, and just see what's left over? Honestly, it sounds like a brilliant idea on the surface.
But here's the catch. XOR completely fails us here, and here's exactly why. The problem explicitly states that the duplicate number appears 1 or more times. It doesn't strictly say it appears exactly twice. So if your array is 1, 3, 3, 3, 2, well, the number 3 appears 3 times. The entire XOR logic relies on pairs perfectly canceling each other out. If a number appears 3 times, that whole strategy just shatters into pieces. We have to abandon it and go right back to our pointer jumping idea. So back to those pointers, because multiple indices point to the exact same duplicate value, chasing these pointers eventually forces us to revisit an index we've already been to. We form an endless loop. Does this sound familiar at all? It really should. This is identically mirroring a linked list cycle. We have just organically discovered a cycle detection problem perfectly disguised inside a standard array. Let's really lock this connection in. We can map those abstract linked list concepts directly onto our concrete array. In a linked list, you have a current node, right? In our array, that is simply the array index I. In a linked list, you have a next pointer. In our array, that's just the value at that index, nums of I. So, moving to the next node simply means setting our index I to nums of I. It's an absolutely perfect one-to-one mapping. But hold on, before we start actually running algorithms, we need to ask a critical Socratic question about the boundaries of our new structure. We know our array indices go from 0 up to n, but we also know that the values inside the array are strictly in the range of 1 to n, meaning no element in this array will ever hold the value 0. So what exactly happens to index 0? Well, because no element ever holds the value 0, absolutely nothing will ever point back to index 0. You literally can never jump back to it. And that means index 0 is guaranteed to sit strictly outside the cycle. It acts as our perfect uncorrupted starting line. It's the starting tail leading into the loop, which means we're dealing with a cycle that has a distinct entrance. And that entrance is exactly where our duplicate number lives.
So how do we find that entrance? We use Floyd's cycle detection, the famous Tortoise and Hare algorithm. Let's map this out physically. Let A be the distance to the cycle entrance, let C be the cycle length, and let X be the distance inside the cycle where our slow and fast pointers finally meet up. When they inevitably collide, the slow pointer has traveled a total distance of A plus X. the fast pointer, it's traveled a plus x plus some number of full laps around the cycle, which we can write as k times c.
Now, stay with me here because this is exactly where the magic happens. We know the fast pointer travels exactly twice as fast as the slow pointer. Therefore, 2 times the slow pointer's distance, which is 2 times the quantity a plus x, must equal the fast pointer's distance, which is a plus x plus k times c. It's just a simple algebraic equation, but guys, it holds the absolute secret to this entire problem.
If we simplify that equation by just subtracting a and x from both sides, we get this incredible realization: a equals k times c minus x. This is literally the massive aha moment of our explainer. But I know looking at raw algebra isn't always super intuitive. What does a equals k times c minus x actually mean for us out in the physical space of this array?
Translated into plain English, it means exactly this. The distance from our starting line, index 0, to the cycle entrance is exactly equal to the remaining distance from our meeting point to finish the loop. Just think about that. If we walk from the very beginning and simultaneously walk from our meeting point inside the loop, taking just one step at a time, those two paths are mathematically guaranteed to converge right at the entrance of the cycle.
With that brilliant deduction, we now have our high-level two-phase algorithm. Phase 1. We start a slow and fast pointer, moving them at 1x and 2x speed until they finally collide inside the loop. Then, Phase 2, we leave the slow pointer exactly where it is. We start a brand new third pointer all the way back at index 0. Then, we move both of them forward at exactly 1x speed. The exact spot where they crash into each other is the start of the cycle. And guess what? That spot is our duplicate number.
We are so close to coding this, but our inner Socratic detective demands one final check. If we start our slow pointer I and our fast pointer j at index 0, and our loop checks if I equals j, how do we stop the code from just immediately exiting on the very first microsecond before they even take a step? This is a sneaky, silent bug that catches a lot of developers completely off guard.
To avoid falsely exiting on iteration 0, we basically need the logic of a do-while loop. We absolutely have to start I and j at 0. But crucially, we must update their positions, make them take their steps, before we ever check if they're equal. Then, moving into phase 2, we initialize our third pointer, let's call it k, at 0, and apply that exact same careful stepping logic.
Just look at how elegantly this translates into Python. We set I and j to 0. We use a while true loop, which nicely acts as our do-while. Inside, we move I one step to nums of I, and j 2 steps to nums of j. Only then do we check if I equals j and break out if they do. Phase 1 complete. Then we set k to 0. We open another while true loop. We move I and k one step each. When they equal each other, we return k. The math works perfectly, utilizing only constant extra space, and we never mutate the original array.
We started with a simple array and a rigid space constraint, and by continually questioning our assumptions, we uncovered a hidden linked list cycle right beneath the surface. It really makes you wonder, now that you've derived cycle detection for an array, what other hidden data structures are just lurking inside your everyday code? Keep those Socratic detective skills sharp, always question the constraints, and never stop exploring. Thanks for joining me on this explainer, and I'll catch you on the next one.